So the work I'm going to present is called gr4-packet-modem. I guess this is an out-of-tree module for GNU Radio 4. It's probably the first out-of-tree module. This is a packet-based QPSK modem, although you could do other modulations as well. It was implemented from scratch in GNU Radio 4.0. This is a project funded by GNU Radio using money from an ARDC grant, as you saw. And the project has been running from May to September, so it's almost finished, but there's still time to do more stuff in September. There were two main goals for this project. One is to test how GNU Radio 4.0 currently works in a digital communications application, because as Eric was saying, it will surely work great for FAIR, but we also want it to work great for all the SDR community. So one goal is to test how this works and to give feedback to the FAIR team about what things work well, what other things can be improved. And the other point is about documentation and easing the way for people to start coding into GNU Radio 4.0. So if you have a set of blocks and if you have a complete application which does something useful, you can use the blocks as examples to do some similar blocks. You can use this application to customize it. So that's the main deal here. When I began this project, the design goals or criteria I set to myself were the following ones. So I wanted to do a modular implementation with many small blocks. This is also the way I work in GR3. And for this project, I think that was really important because, first of all, if you want this to be usable by other people as examples or components of their applications and flow graph, you need this one block per functionality rather than having your whole receiver in a single block. You could do that. You could have a huge block, which is IQ data in, packets out, but then you're also not really testing the GNU Radio 4 scheduler or how buffers work. You're just testing it in a very limited way. So modular, many small blocks. It should be suitable for IP communication. So that basically means having a TAN device in Linux you can send IP data through. And that's for two main reasons. One, it's easy to test out. There are many applications you can use with IP. You can use ping, you can use iPerf to generate traffic and test your system. And it's also flashy and nice feature, and many people want IP. It's like, how do I send network over my radio? It should have good latency. Coming to the previous point, it's no fun if you want to do TCP and there's 10 seconds of latency. And this has been a huge pain point of GNU Radio 3, as in continuous transmitter. If you have DBS2, for example, at low symbol rates, it's difficult to have good latency. The packet size should be flexible. Any packet size should work. Because I wanted to test latency at any different packet size, and that unfortunately means there is no FEC for the payload, because if you define an FEC which is good, I don't know, an LDPC code, then it pretty much ties you to one particular packet size or set of packet sizes. So there is no payload FEC, but there is the provision. If the user wants a fixed packet size and his own FEC algorithm, there's a place to put it. It should use good signal processing techniques, like we're having these packets, they have a preamble, so we should use FFT to detect the packets and synchronize, rather than saying, oh, but I have my Costas loop, and I need to have a long training sequence because you know, the bandwidth, and it doesn't log. It should be production ready, and by that I mean it should run without crashing and anything, and you should be able to go and deploy this in some application, maybe a simple application in industry, where everything is good enough that people will say, yeah, that's good, besides that there is no FEC on the payload. So if you put there an FEC, this should be a modem you can use in production. There is only QPSK for the modem for the moment, mainly for simplicity, but there is also places where you can set your own modulations and codings. If payload FEC is added, this should work at low SNR. So if I add my own LDPC code or anything, then everything else in the modem should be up to the same level of the LDPC code. So the modem should synchronize, it should decode the header and everything else. The payload FEC decoding should be the point at where it breaks if I reduce the SNR. And the modem should also support in the transmitter 2 different modes, which are burst mode. That's when I have 1 packet to send it, I send it. If I don't have anything to send, radio silence. And also stream mode, which basically emulates how DVB-S2 and similar protocols work, which is whenever I have a packet to send, I send it. Whenever I have nothing, I keep my carrier, I keep my transmission, I keep sending idle frames. And that introduces considerations for latency. Waveform design, I want to go through these very quickly. So it's the most simple design you can imagine for this. Single carrier, RRC waveform, QPSK. The packet has a sync word, which is 64 bits. I've taken many of these ingredients from CCSDS because I come from the space community and I think these choices are nice. So CCSDS sync word. Then there is a header. The header has 32 bits of information. The most important thing in there is 16 bits indicating the packet length. And then there is provision for modulation and coding packet types. So if you want to extend the header, you have room in there to say, I have this mod code, I have these different packet types. You could have virtual channels, whatever you can dream of. Since the header needs to be decoded at very low SNR, and the goal was something like 0 dBs ESN0, I think, there is an LDPC code which I designed just for this application because FEC coding for short block sizes is tricky, and then there is also a repetition code on top of that. Then we have the payload, it's QPSK or other modulation, it's variable size. We have CRC32 for the payload, and then there is this ramp down sequence. So what happens when you have this burst modem, it's not so important if you are using an RRC waveform, but if you want to replace that by something like OQPSK, which is constant envelope, then you want to ramp up the power and then ramp it down at the end of the packet to prevent those power amplifier clicks on the spectrum. So there is the ramp down, basically so that you already see how that can work as part of the system. This is the flow graph of the packet transmitter, and this is how you would see the flow graph in GNU Radio Companion if there would be currently GNU Radio Companion support for gr4. So everything in here is a block in the flow graph, and you have all the connections. This is actually how the flow graph is in C++. So I'm going to go through these very quickly. There is much more documentation about how the modem works in the GNU Radio wiki. If you search for gr4-packet-modem, there is like theory of operation, and you have the description about what each block is doing as part of the system. So to go very briefly, packets coming here on the packet ingress. Then you send a message to this header formatter for each packet because you say, I need you to prepare a header for this packet size and perhaps for this packet type, for this modulation, whatever. And then you treat the header and the payload on separate tracks. You have the CRC. You might have the payload FEC. So this is not implemented, but if you implement it, you should put it here. Then there is this packet mux, which is concatenating header and payload. You unpack. There is this scrambler. I didn't mention it, but in any kind of modem, you should have scrambling. The header is generated as a vector source, which keeps repeating the sync word is generated as a vector source, which keeps repeating the sync word pattern. And then you have these mapper blocks to modulate, so to convert from bits or pairs of bits for QPSK to complex symbols. These things in yellow are only present in burst mode, so all of this is about the tail at the end of the packet for the ramp down sequence. And then you have these packet mugs to group all the symbols together. This thing in blue is for stream mode. So for stream mode, basically you are converting your PDUs. I'll come to that later, how this is organized in packets. So there are PDUs, as in gr3. So you are converting your PDUs into a tag stream that it's a continuous stream, and you can send it to an SDR. Then you have this interpolating FIR filter, which is your RRC filter. And only in burst mode, you have this burst shaper, which is the one applying the amplitude pattern. For the receiver, as I mentioned, the first thing the receiver does is to do an FFT correlation with the sync word to detect the presence of the packet, estimate everything you can estimate, so amplitude, phase, frequency, timing, which is the sample in which the packet starts, and also the fractional sample delay, because you want to be very accurate doing matched filtering on the receiver. Then you correct the frequency error you have estimated, and you correct for the amplitude. Then you do an RRC filter and down sample to 1 sample per symbol, and this is open loop. So you have estimated with the synchronization word where the packet begins, and you keep throughout the whole packet at the nominal symbol rate. So there is no closed loop recovery for symbol timing. For phase, there is closed loop recovery because you really need it in this kind of system. So there is a Costas loop. The Costas loop is seeded with the phase estimate from the sync word. So it logs really fast and really well. And then it keeps tracking phase through the whole packet. So it must know what is the constellation for the payload and for the header and everything. And the sync word is used as pilot symbols because that's a known pattern. So this is how the flow graph looks like. We have the sync word detection, then we have this coarse frequency correction, symbol filter, the sync word wipeoff, so that's where we remove the changing pattern of the sync word. And here we have a very important block, so I will make emphasis here. This is called payload metadata insert. So what happens with this block is that at the beginning of the payload, it's going to insert a tag saying a few things about the packet. What's the packet length, what's the packet modulation, etc. Because the blocks down the chain need that information. However, what happens is this information is actually contained on the header for the packet. So until I do not decode the header for the packet, I cannot process the sync word. I cannot process the payload because I don't have that information. I cannot insert that tag. So what happens is the packet comes along. This is going to pass the header to the output. The header will go through the whole demodulation chain. It will be processed. I will come back to that in a moment. And once the header is decoded, we have this header parser, which is interpreting the information on the header, making a message with packet length, modulation, packet type, whatever, sending it back to the payload metadata insert, which is blocking. It's not sending any of the payload symbols downstream, but when the message comes here, then it can add the tag onto the output stream and begin sending the packet payload. So that's how it works. And for demodulation, we have the Costas loop. We remove the sync word here because we do not need it anymore. It has already trained the Costas loop. We have the constellation LLR decoder. So you go from complex symbols to basically log likelihood ratios for the bits, so soft bits if you wish. This is an interesting block because it's only implemented for BPSK and QPSK at the moment. You could add any constellation you want. And the interesting thing about it is that it changes the interpolation factor at runtime depending on the constellation. Because if you think QPSK is one symbol comes in, then you have 2 bits coming out. 64 QAM would be one constellation symbol coming in, something, 4 bits coming out, or whatever, or 6 of them. So yeah, that kind of works with the current gr4 runtime. There are some rough spots just when the change happens, but it almost works. Then you need to descramble. There is the header payload split, because again, header and payload go through separate tracks. You FEC decode, so there is the LDPC decoder for the header. And on the payload, if you are doing any FEC, you would put the FEC decoder here. And finally, you do a binary slicer to obtain heartbeats. You pack 8 bits per byte, CRC check, and if the CRC is okay, you say, here's my packet. So this is how it works. The complete modem can be integrated in any kind of system. So here I have an example of transmitter and receiver using SDRs, but you could also do like only software loopback simulation with channel model in the middle. There is also an example like this, and you can run it right away. If you have a Linux machine with Docker, you can Docker pull this gr4 modem, whatever, and there is a quick start guide on the README, and you can run something similar to what I'll run in a second now. So basically, you have your ton source. This is where your IP packets come in. You have the packet transmitter, and then there is something to control latency. So basically, this is Matt Edu's talk in GRCon 2019. He was speaking about how to manage latency by limiting the number of samples or packets that go into some part of the flow graph. So basically, when some packet goes out to the SDR, a message is sent back to the ton source saying, OK, this packet is clear, now you can send more stuff. Because if we do not limit the amount, if you try to send a lot of IP packets, then basically the packet transmitter gets full of thousands of IP packets in buffers, and you have hundreds of seconds of latency. So there's something that needs to be done. Here it's done at the flow graph level with blocks which are aware of this. Maybe a custom scheduler which knows when not to call the ton source because there are already enough packets in the flow graph would also help here. So that's an interesting concept to experiment with. And finally, you go to the SDR. On the receiver, it's easier. Oftentimes, latency is not so critical on receivers for these kind of systems. So basically, SDR, packet receiver, there's this packet type filter because you need to throw away idle packets. And finally, you go into the ton sync. So now there's the demo. And here on the table, I have 3 SDRs. There's a USRP, which is going to be the transmitter. There's an RTL SDR, which is going to be the receiver. And I also have a Pluto SDR, which is running my SDR. You can see it here. That's basically to see the spectrum. The way I'm going to run this is for the receiver, everything is GR4. So there is already a SOAP block. It can run with the RTL SDR, 2.4 megasamples a second. 4 samples per symbol, so this is a 600 kilosymbol thingy, and this laptop is 13 years old, so this is not a new machine. On a new machine you can run faster symbol rates and nicer things, right? So transmitter, what I'm doing is there is not a transmitter block for the USRP on GNU Radio 4 at the moment, so I have something which writes on a FIFO. And then there is a GR3 flow graph which reads from the FIFO and basically writes on a UHD sync. So I'm going to run this is the GR3 flow graph which reads from a file. In this case, it's a FIFO and writes to the UHD. I also have these plot symbols, so come back to that in a second. This is some simple Python script which receives symbols from the gr4 modem through 0MQ and plots the constellation. Just because we don't have any GUI blocks within gr4 at the moment, so that's a simple way to plot your constellations. Then I have my transmitter, so I basically say packet transmitter right onto test FIFO, and probably I can move this to the other window. And next I have my receiver. So it says it's found the RTL SDR and I think it's going. So if I run a ping here, maybe a word about pinging myself, because this is a single machine, so I'm using Linux network namespaces to ping myself through these whole radios, because otherwise if I say ping yourself, Linux will say, yeah, this is a local IP, there you go, and not send anything to the radios. So you can see ping is going, you can see the packets there. Latency is about 100 milliseconds, which is good, not great. I think most of that is because of the FIFO, which is connecting to gr3, and also because of this laptop. If I run this at home on my much more capable desktop machine, it's 50 millisecond latency, I think. Also here in the modem, you can see there is this user data decoding, so you have like all the information in the header. Something else we can play with, so you can see here the constellation, and now it's very clean. So what I can do here is drop down the amplitude, and now it is horrible. So basically we don't have any FEC on the payload, so the ping is no longer going, but you can see packets are still detected, and you can see the correct packet length. So the LDPC on the header works even with this very low SNR signal. If you add a nice LDPC code on the payload, it will also work. So I think I had something like 70 here. Something else I should show is iPerf, because this is mainly the way I test like the system end to end. So basically iPerf, I'm sending TCP data, and you can see there are a bunch of packets. Probably I should close this Python script, because plotting many packets with Python is not the best idea. But you can see the signal here. This is like an average power plot. So now that we have a continuous stream of packets, you see a stronger signal. And you can see basically this is working. It's doing 1 megabit per second. There are some retransmissions, but probably no packet loss. So this is working. Something you can notice is the RAM usage is slowly increasing. If I keep this going for a longer while, then I might eventually run out of RAM. So that's one of the things that currently needs to be fixed. And probably here I've hit one of the receiver bugs. So you see the TCP is no longer going, basically because it has sent one packet and it's not getting any replies. There is currently some bug we are working with the FAIR team to solve about buffer state corruption that happens at some point. So
Daniel, yeah. Hi. Can I ask something? That's great work, by the way. I'm just curious if you can start iPerf transmission again and adjust with the receiver gain while the packet is coming to see how much it can compensate for amplitude variation. Because I understand you didn't use any automatic gain controller or whatsoever, so it may disrupt Costas loop and
good point.
You know,
so
yeah.
Within the packet, it doesn't compensate for amplitude variations. It takes the amplitude at the beginning of the packet. So if you have a very sudden amplitude change throughout a single packet, which is short, then that packet might fail to decode.
Okay.
But you know,
but for the rest of it, it's
the next packet takes
next packet is different.
Correct amplitude. Do I have some more? 5 minutes? Yeah, great. So yeah, I basically want to give a few feedback notes about what I have learned through this project about gr4. So nice features. Process bulk calls are chunked using tags. So if you have a tag, you are guaranteed to have it on the first sample of your call, with some exceptions. And that's nice in many blocks. It simplifies the implementation of the block, but it's maybe too much overhead in some other situations where you don't even need to look at tags. So perhaps it should be an opt-in feature, I don't know. Something else I'm doing, and I think this is not really the way it's intended to be done, but I think this is nice. You can use messages with regular ports rather than with message ports, because you can have regular ports with any data type. So that data type might be a message as well. And the reason I do this is because with gr3, often you have a block that receives a message, and then you want to use something about the message in the work function. So you need to store it somewhere else, because basically you have two functions. In here, you're going to have your work function, and the message comes in through a regular port, and the data's already there, and you can use it. So for me, that's been much nicer, and it works. So something to think about. Also, rational resampling ratio. We have it as a first-class citizen on gr4. In gr3, you only have decimation and interpolation. So that's nice. And the history buffer, I think, is fantastic, not only as a replacement of gr3 history, but also for other stuff. For example, in the FFT detection block, I use it because if I see a correlation peak, I cannot say, OK, this is a packet, because maybe 10 samples afterwards comes a much larger peak. So I need to wait on. And I wait on through a history buffer, and I put all sorts of metadata in there. So that's great. Some shortcomings I found: tags are too expensive. So on the packet transmitter, I was at first using a packet length tag at the beginning of a packet, so kind of a tagged stream thing, and it didn't work properly because it was so much overhead. What we can use instead is vectors. So that's called PDU on my code. It's called packet on core. Basically, it's a standard vector where you put your packet. There are some maybe not nice things with that. So by default, you get buffers which are 65K elements, and maybe you don't want to have 65,000 whole packets in your buffer. You could have smaller buffers, I understand, like even 2 elements in the buffer. With these large buffers, there is a lack of back pressure, because the buffer only fills up with 65,000 packets. And then something about memory management. So you have these standard vectors rather than scalar types. Who deallocates the unused packets? Is it constantly allocating, deallocating? All sorts of questions for me. Also general blocks. So there is no forecast function at the moment, and it is not foreseen. There is an async port, which means this port might do anything regarding resampling. And in most cases I've used it, it works, but it might not be enough in some cases, I think. Coming from gr3, there are some cases where forecast has been really important to make the block do exactly what I wanted, so I'm not really sure, especially when you have a block that sometimes can produce output without an input and sometimes cannot. So how do you communicate that to the scheduler? Also something else, there is the single-threaded scheduler, there is the multi-threaded scheduler. The demo you saw before is single-threaded scheduler, and the reason for that is multi-threaded scheduler crashes with most of the flow graphs I've written. And I don't know why. It's basically some tag that should have arrived doesn't, so the block crashes. And then there is some buffer management bugs, and you saw one of those in action. And finally, a fun experiment we did. So this was with Frank Seppenfeld from ESA, not ESA Germany, but ESA Netherlands, ESTEC. He works with the satellite communication group, and he reached me in the summer saying, oh, we have 1 megahertz of geo-transponder bandwidth because we are doing some tests with industry. Would you like to test your gr4 modem on the satellite? And I said, yes. And the way this works out is they have everything for downlink set up at a German ground station with a very large antenna, but you need to do the uplink on your own. This is 5.9 gigahertz, so here am I at home with my Wi-Fi antenna, 2-watt Chinese power amplifier from AliExpress, and you can imagine the SNR you get out of this is not very good, so this was 125 symbols per second to get an SNR of between 9 and 10 dBs, which is the thing you need to decode with no FEC, some short ping packets. And then the interesting thing is this is 5.9 gigahertz with this USRP, no GPSDO, no nothing. So the frequency oscillates like crazy, and I needed to tweak all the Kostats loop parameters, but it worked great. I was like testing at night and, you know, change, recompile, run, and it ran. I will put up the SIGMF file of this probably this afternoon for all you to play with. And that's all I had.